Kiddies, welcome to chapter 5. We're going to talk all this section or this chapter about linear functions. So it's all going to have to deal about lines. So what the heck are lines? That is Dragging the Line by Tommy James and the Shondells way back from the 60s. Check them out. You might like them. Kind of very close to Fetty Wap in case you might like that guy too. So today we're going to talk about section 1, plotting points on a coordinate plane. So this is really going to set up what we're going to talk about within this chapter. So let's jump right into it. First thing we need to talk about is what is a coordinate plane. So here what I have is what's called a Cartesian plane. Sassy name there. Something maybe you have recognized or seen in the past. So I just want to go through some fine details about what a coordinate plane is. So a coordinate plane is a way to show two-dimensional space, and I don't mean to confuse you by that, but notice how we have really two lines here, the black lines. We have the left and the right and the up and the down, so it really shows us two dimensions. Okay, what we call these are the axes. Specifically, the one that's left and right is known as the x-axis, or axis, I'm sorry, and the up and down is known as the y-axis. Okay, so if you think back to when we talked earlier about functions, way back in chapter 1 about inputs and outputs, we use this idea of x and y. So if you remember inputs that lead to outputs, we use x to represent inputs and y to represent outputs. So on this coordinate plane, we're able to show where these inputs and outputs are at the same point. So for example, when we are given an x and a y, we're going to be given a point. Okay, so say I have a point right there, a point in this plane. What that point means, if you look at it, well, the point is 2 units over on the x-axis and 3 units up on the y-axis. So what we get is this point. So it shows us a relation between the inputs and the outputs. That's a lot of confusing stuff, okay, a lot of confusing jargon. Just a couple more things about this coordinate plane. When we look at the x and y axis, notice that we are shown kind of this point right here where those two axes intersect. This point right here is known as the origin. Okay, so the origin is the point where your x value is 0 and your y value is 0. So it's at a point of 0, 0. Now, as I go through this, notice that I wrote down this notation for labeling a point. When I get a point like this that I had labeled before, we always label a point using parentheses. So I have a close parentheses, a comma, and what I do is I look at my input versus my output. Now, how you're going to see this labeled is x, y. So anytime I get a point, I'm going to start with my input or my x first, and then I'm going to write my output second. So in this case, if I have this point of 2 over on the x and 3 up on the y, I would label this point as 2, 3. So those two values represent where exactly this point is. Notice when I write this that the x value comes first. When I went 2 to the right, that came first. My y value 3 up, that came second. So always, always, always in points, it is x first followed by the y. So now what I expect you to do is if I were to give you then a random point, let's say then I use point P, and I say that this point is at a value of, making up numbers, 5, 3. How would you be able to identify where that point is? So what you want to do is on this axis, you're always going to start from the origin. The origin is always where you're going to use as a reference point. Okay? So from this, I know from my origin, I'm going to move 5 units, okay, 5 units to the right. 1, 2, 3, 4, 5, and then 3 units up, so right there. So that means my point is going to be, I lost count, 1, 2, 3, 4, 5, up 3, right there. So that would be point P. So if I give you points or if I show you points, first thing I'd be able to do is recognize where those points are. So let me give you another example. If I said point R, say R was at 0, negative 4. How would I plot that? Now remember, numbers are not always going to be positive. Notice that we have these different regions of this graph. So first of all, I have 0. So that means, what does that mean? I guess is I start from the origin, and the first number represents how far I move in the x direction. So left or right. This says 0. So does that mean I move at all? Well, I move 0 units, which means I stay right here at the origin. But now I move negative 4. Notice the last 2 examples I gave you positive numbers, and 3 represented moving up 3. So if you think about it, what does negative mean? Negative means you're going to move not up, but down 4. So point R is going to be at this location right here. So that would be point R, which is at a point of 0, negative 4. So it brings up my next point. On this coordinate plane, the right side of this axis, the x, is the positive x direction, and anything to the left is the negative. Same thing with the y. Anything up is positive, anything down is negative. Okay, so if you see points that are positive or negative, you have to know which direction they go. And this really shows that in our graph we have really 4 different regions. What these regions are called quadrants. So on a graph there are 4 different quadrants that we could find points in. Okay? And it starts here from this region. This is the region that we like to use a lot because both things are positive. So this is called quadrant 1. I'm going to use that with a Roman numeral, quadrant 1, not quadrant I. Going this way then, it goes in counterclockwise rotation. This one right here would be quadrant 2. This is quadrant 3. And this is quadrant 4. So let's say I were to give you the point of, let's say, point M, which is at negative 2, negative 3. So if you plotted that point, you would start from the origin. Negative 2 means you're going to go 2 to the left. Negative 3 means you're going to go 3 down. So it would be located at this point. That would be point M. So one thing you have to be able to identify is which quadrant that point is in. So if I plot that point, I know that this M is in quadrant 3. Okay. You can also identify that by positive and negative, but one easy way to do it is you can just plot the point and tell which quadrant it is. So I went through a lot of vocab here. Hopefully you wrote all this stuff down. You need to know the axes. You need to know positive and negative. You need to know how to label points. You need to know how to find points, how to draw points, where they are, and you also need to be able to identify the quadrants. So what we're going to look at this chapter is we are going to be looking at what are called linear functions. They are functions that, as a result, form straight lines. So one thing you're going to have to be able to do is recognize where points are on a line. So if this is a graph, if this is a function of a line, how do I identify points? Okay, so remember, points are values of x and y. And on this coordinate plane, on this grid, you'll see regions where this line goes through a perfect intersection. Okay, so right here, for example, at the start, I'll use a different color than red. Here is another point where they cross perfectly. Here is another point where they cross perfectly. Right here as well. Here as well. Here as well. And go on, right? But you can see that where these lines cross, they cross at an exact intersection of this grid. These right here represents points on a line. They're perfect points. So if I were to identify these points, starting with, I'll start with this one. This one would have a point of 0, 4, 0 right and left, 4 up. This one went 2 to the right, 1 up. This one went, 4 to the right, and then 2 down. And what these values represent is they represent specific points on this function. So there's a bunch of points, but right now I've shown really only 3 of them. But from these points, we get a relationship. And we've done this before in Chapter 1. remember how we looked at a relationship between inputs and outputs? I would ask you guys, how do you get from 0 to 4? How do you get from 2 to 1? How do you get from 4 to negative 2? Okay, so that's kind of what we're going to be doing and focusing on this chapter is we're going to look at these different relationships between these points. But all we're going to be looking at is a linear relationship. Another thing to realize or understand is, I don't know if you noticed as I was drawing the points, but notice how the points that I chose that were at the perfect intersections, do you notice that they are perfectly spaced apart? Okay, so there's a spacing, there's a perfect spacing between these points. It's not random, but it ends up working out that there's a perfect spacing between them. And that's one of the things we're going to look at because all functions are relationships. They're working relationships, and our goal is to be able to identify those relationships through the points, and the opposite of that is being able to, given that relationship, figure out what the points are going to be. Okay, so let's go ahead and take a look at a word type problem. So this is just going to be a little application of all the things we're going to be doing. So what you have is, it says Sarah has 2 baseball cards, and each day she collects 3 more cards. So really what we're looking at is we're looking at a relationship between the number of baseball cards she has and, I guess, each day. So there's really 2 things we're looking at, baseball cards and days. And what we're going to do is try and represent the relationship between these 2 things. So first of all, we can represent this relationship through a table. By doing that, remember that we are going to have in our table a list of inputs and a list of outputs. We've done this before. What we have to figure out is what are inputs and outputs. Well, we have 2 things. We have days and baseball cards. If you think about it, the number of baseball cards you have is represented by each day. So you think about this input. The input is really going to be represented by the number of days. And after a certain number of days, Sarah's going to have a certain number of cards. So I'm going to think of this in terms of input and output. So we can think through this table, okay, after 0 days, what does 0 days mean? Well, that's how many cards does she start with? Well, it says in the problem that Sarah starts with 2 baseball cards. So our initial value is going to be 2. We know that she starts off with 2 baseball cards. And this is one thing we're going to be looking at in these functions or in these relationships is what is the initial value? And what we just found out here that the initial value in this case is 2 cards. So the initial value represents how much you already start with. You could start with something, as in 2 cards. You can start with nothing, as in 0. Or you can start by missing something. But in any of these functions or any of these relationships, the initial value is going to be what we start with. The next thing we're going to look at is what happens each day. Well, it says each day she collects 3 cards. So think about after 1 day, how many cards would she have? Well, if she adds 3 cards each day, 2 plus 3 would give me 5. And then the next day, 5 plus 3 will give me 8. And 8 plus 3 would give me 11. And if you look at this, how do I figure this out? Well, each day I'm adding 3 cards. And you should see a pattern here. Each day I'm adding 3. Each day I'm adding 3. This right here that says each day she added 3 cards, this represents what's called the rate of change. Rate of change is simply how much something is changing over that given amount of time. So we know that she is gaining 3 cards per day. Okay, so 3 cards per day. Now the tricky part that we did a while back was then trying to take this thing that's shown in the table and write an equation. Well, I'm going to show you an easy way to do this to start off. My equation is going to represent y. Y represents my output. So it's always going to tell me how many cards I have. The number of cards depends on the number of days. So remember that we label our outputs as y and our inputs as x. So here's how you're going to write your equation. You're going to start first with your initial value. I know that I start off with 2 cards. So I'm going to have y equals 2, and every day I'm going to add to that 3 cards. So that means I have 3 cards per day. When you see that, how you're going to write that is 3. Now, we don't know necessarily the number of days, and the purpose of this equation is we can put any number of days. I could ask you after 15 days. So instead of writing the number of days, we're going to label the number of days as x. So I get y equals 2 plus 3x. This represents my equation and shows the relationship again between my outputs and my inputs. That is the function that shows that relationship. And you can check this. If I use this equation, y equals 2 plus 3x, let's say I want to know the number of cards after 4 days. Well, yeah, I can fill out my table, but what I can do here is that if I know y represents the number of cards and x represents the number of days, I can then take this equation and plug in, oopsies, and I can take and plug in 3 times 4, 4 representing the number of days. Someone's knocking at my dang door. Hold on, folks. All right, back at it. Sorry, for you guys it's probably just like a half a second pause. But back at this, we're going to try and solve again for the number of cards. So to simplify this, I'm going to take 3 times 4, which is 12, add to that 2, and I'm going to get y equals 14 cards. So that means after 4 days, hey, I'm going to have 14, or Sarah's going to have 14 cards. Check back to this. Notice how if I ended at 3 days, 4 days would be the next one. How many cards would I have? Would be 14 if we follow the same pattern of adding 3. So notice how our equation allows us to simplify things a lot easier than just using a table. Okay, then the last thing is what I want you to be able to do is take these values and graph them. Now, if you look at this table, each of these represents a point of x and y. So you have 0 for x, 2 for y. So each of these represents points. I'm going to write the points down here. So my first point is 0, 2. 0 days, 2 cards. 1 day, 5 cards. 2 days, 8 cards. 3 days, 11 cards. And what I can do now is plot these points. So on the graph, let me zoom in here for a second. Whoa. I can plot these points. First one, 0, 2. It means I start at 0, I go up 2. That point would be right there. Next one, I have 1, 5. So I go right 1, up 5. It's going to take me to right here. Is that right? 1, 2, 3, 4. Ah, you dingus. That's 4, folks. I tell you sometimes, huh? The next one would go up, right 2, and then up 8. So we're going to go all the way to the top here. Now, I ran out of space for the last one, 3, 11, but calm down. But I want you to think about this. If you plot the points, and I get my 3 points here, connect the dots. I'm going to connect them with a red line. I'm going to connect them with a line that would look like that. Now, again, I kind of said it, and I was going to ask you guys, but when I connect those points, what does it form? It forms a straight line, and that's exactly what we're going to look at this chapter. A lot of things I did in this one problem, a lot of things we're going to do throughout. We took a problem, we made a table, we came up with an equation, we plotted points, we drew a line, and that's kind of the things we're going to be doing. And these are what linear functions are, is relationships that form a straight line on a graph. Okay, next type of problem is I want to know, is 5, 8 a solution to y equals negative 2x plus 3? Now, we did this before. We did this way back in chapter 1. How do I know that this point of 5, 8 is a solution? How do I know if something is a solution? Remember that the value of 5 is x and the value of 8 is y. So how do I know if something is a solution? If you remember back, if I plug 5, 8 back into the equation, if what I get is true, then it's going to be a solution. So if I take these values, and I'm going to take 8, and I'm going to plug 8 in for y, and I'm going to take 5 and plug 5 in for x. Let's see what I get. So I'm going to have 8 equals negative 2 times 5 plus 3. So solving this, I get 8 equals negative 2 times 5 is negative 10 plus 3. So I'm going to get 8 equals negative 10 plus 3. That's negative 7. So does 8 equal negative 7? No. So is 5, 8 a solution? What do you think, kiddies? Doesn't work out? No, it's not a solution. Now, what I'm going to do is show you this graphically. Okay? What I have here is I have this function of y equals negative 2x plus 3, and I have all these values of x. So if I give you the function and I want you to find the values of y, what do? Well, you're going to take each of these values of x and plug it into your equation. I'm going to show you guys a couple of them. So down here I have y equals negative 2. I'm going to take the first point of x of 0 and plug that in. Well, negative 2 times 0, that drops out, and that's going to give me y equals 3. So I know that when x is 0, y is 3. Do the next one. When y equals 1, I'm going to plug in negative 2 times 1 plus 3, and let's see what I get. Negative 2 times 1 is negative 2. Add that to 3, and I'm going to get 1. So when x equals 1, y equals 1. And I'll show you one more, and then we'll talk about something. I get y equals, next one is negative 2 times 2 plus 3. So again, I plugged x in for x, or 2 in for x. Multiply these together, I get y equals negative 4 plus 3. And that's going to tell me y equals negative 1. Okay, so now I get negative 1. So now if we just take a look, let's pause and look. If you remember back to the last slide or last example, we noticed the pattern. Now you may not notice it right away, but think about it. How do I get from 3 to 1? Well, what I did is I subtracted 2. How do I get from 1 to negative 1? I subtracted 2. Notice how we have our initial value plus 3. Well, hey, that's my initial value right here. When x is 0, my initial value is 3. And notice that negative 2x, this is my rate of change. So it goes down 2, down 2. That's my rate of change. So we can fill out this table without even doing the rest. I know that from here on out, it's going to be minus 2, minus 2, minus 2. So now let's fill it out. If I have negative 1 and I take away 2 more, I'm going to have negative 3. If I have negative 3 and I take away 2 more, I'm going to have negative 5. And take away 2 more, negative 7. What I get are those points. So if I recognize a pattern, I can plot these points easily. So now if I plot these points on my graph, I'm going to have 0, 3, which is going to be here. I'm going to have 1, 1, which is there. So I'll try and make these a little clearer. 2, negative 1, which would be here. Then I have the next point, 3, negative 3. The next point would be here, 4, negative 5. And then 5, negative 7 would be there. So I'm going to have all these points. Again, I kind of went through that quick, but you can check those. Notice what they form again. When I plot these points, if I were to draw a straight line between these, or what they should form, is, and let me just kind of slide this across, move it, oopsies, whoopsies, whoopsies, oh no. Oh no. There we go. Gosh, that was painstaking. But notice that those points form a line. Sorry for moving the screen on you. It probably just blew your mind a little bit. But notice how this point, 5, 8, I'm going to show you one last thing here. 5, 8, if I plot this point, that is going to be 5 to the right, 1, 2, 3, 4, 5, 8 up. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8 is all the way over here. Well, that's a nasty point, okay? But this is the point of 5, 8. What do you notice? Why is it not a solution? Well, it's not a solution because it doesn't fall on the line. Okay, it doesn't fall on the line, therefore it's not a solution. So in order for a point to be a solution, one either makes the equation true or the point needs to fall on the line. If it doesn't, it's not a solution. All right, let's go ahead and do the opposite. Now I have a graph, that's kind of funny. I have a graph for you with all the points shown. I want you to go ahead and fill in the table. So I'm going to look for what is my y value and my x is negative 3. So I'm going to look here, okay, x of negative 3, that means I'm going to go left 3, so 1, 2, 3. What's my y value? Well, if this is my x value of negative 3, how do I find y? That means I have to go down and figure out where is my point when x is negative 3. And I see it's going to be this point right here. So what is that y value? Well, I went 1, 2, 3 to the left, 1, 2, 3, 4 down. So I went 4 down. That means my y value is negative 4. I can do the same thing. Where's my value for negative 2? I'm going to go 1, 2 back. I see my point is there. It went 2 down. So it went negative 2. Next one, I have negative 1. Go negative 1 means I go, oh, there it is. There's that point. Go 1 back, boom, right there. So what is my y value? Well, it's on the axis. What's y when it's on the... Oh, wait, it's 0, right? I didn't go up or down. It's still on the axis, so that means 0. Now I'm going to pause here for a second. Notice what's the pattern. Notice the rate of change. Negative 4 to negative 2 would be plus 2. Negative 2 to 0 would be plus 2. So if we check the other points, we should see that it's going to go 2, 4, and then 6. Let's check. So I go then at 0, 2, bingo. 1, 4, bingo. 2, 6, bingo was his name-o. Right, so notice that with all these linear relationships, you see a pattern. Okay, a lot of meat and potatoes in this, but it's a lot of skills in this video that you're going to need for the rest of the chapter. So if you have any questions, make sure you jot them down, bring them to class. We'll talk about them. Otherwise, good luck on your practice, and we'll see you guys on the flip side. Peace out, my friends. Dragging the line.